Okay. Recording is started, and so now let's annotate this graph. If that's A, then over here is A plus H, and it's this gap from here to here that is H. And as you make H smaller, it brings the second point closer and closer to the first point. What we're trying to get is the instantaneous slope. I'll actually go more like this. Right here. Trying to get that. But what we will get is, at first, we'll get the slope. Well, let's make that point over here. Well, let me make that a little better. We'll get this slope, which we'll say is a crude approximation of the slope of the red line. As we make H smaller, let's say we make H half the size, we get a much better approximation. As we make it smaller yet, we go to here, we get even better. Closer and closer to the slope of the line that we're really after. Alright, so give me some feedback. Tell me what's the easiest part for you? Is making the definition the easy part and making the picture the hard part, or vice versa, or you're really comfortable with both, or give me a little feedback on the chat. Alright, number 2, find f prime of x. Now, the derivative, we're going to be looking at it a little bit more globally in this practice quiz problem. Find it without any computations. Think of more of what the derivative represents. So without doing a single computation, you should be able to come up with, I think f prime of x is equal to, and give something there. And then, using the definition, f prime of a given above. Alright, so let me give you a minute to do 2a. So you're going to hear some noises here at my house there. Again, they're still re-stuccoing my house. At least there's no pounding. Okay, anybody need more time here on number 2? All right, let's go for it. So the derivative represents the slope. And this is a straight line. F of x equals 7x. And its slope is 7. So the instantaneous slope everywhere should be 7. Now, when we do f prime, Now, we really don't know how to do f prime of x. We know how to do f prime of a. So let's do a according to the definition right up here. It's the limit as h approaches 0. I'm going to write this formula right here, f of a plus h. But what is the f function? F is 7x. Let me rewrite that. Really means f of anything. 7 times that anything. So f of a plus h is going to be 7 a plus h. So just thinking from here, straight down to here. Minus f of a is 7a over h. This is the limit as h approaches 0. 7a plus 7h minus 7a over h. And the 7a's kill each other off. The limit as h approaches 0 of 7h over h, and the h's cancel off. And then that 7 is not bothered by h anymore, so it's just 7. And that gives me exactly the same answer that my intuition was telling me, hey, the slope everywhere is 7, so at any particular point this derivative has to be 7. Now that's f prime at a. But the a could be anything. It could even be x. And so it's the same as f prime of x equals 7. F, the derivative, as a function, and this is what we're going to be getting into in this section, is looking at, that's the title of today's lesson, the derivative as a function of x. F prime of x is it's always 7 everywhere for a line of slope 7. Alright? There's some abstractions involved with this. So give me feedback on this. Back in the chat channel. Okay. Let's do it again. Part B. F of x is 5. Without any computations, think of what f prime of x is going to be. And then do the computation like we did over here for either f prime of x or f prime of a, either one. All right, anybody still need more time with this? Then let's look at it. F prime of of x. Well, this is a horizontal line at 5, so its slope is 0, same as f of x equals 0x plus 5, so I'd expect the derivative is 0 everywhere. And then if I use the definition, and I'll just go with x, realizing my x is replacing my a over here. And then I'm going to do the limit as h approaches 0. F of x plus h, which is going to be, but f of anything is 5. F of x, well, f of anything is 5 over h. That's 0 over h, which is 0. And that agrees with my answer. Okay, let's go ahead and go to C. Same idea. Anticipate what the answer is by thinking of what it represents, and then do the computation. Okay, anybody still need more time with C? Alright, then let's look at it. We'd expect the derivative to be the slope, which is 6. And if we do f prime of x equals the limit, h approaches 0. So imagine this formula up here, but all the a's are replaced with x's. And then f of a, well actually let me write it out again. F of x plus h minus f x over h. So now, f of x plus h is 6 times x plus h minus 4 minus f of x is 6x minus 4 over h. Alright, so this is going to become 6x plus 6h. And then this 6x and this 6x will cancel. This 4 and this 4, because there'll be a double negative there, will cancel. And then what I'll have is, equals the limit h approaches 0, 6 h over h, the h's cancel, and I get 6, which is exactly what I expected. Alright, so let's go to questions. And there was a question that was put up here earlier. problem number 35 on 3.1. And so that's page 138. And let's get the instructions as well as the problem. Okay, so we'll do 35 and the following, it says find f prime of A. And we're going to use, it doesn't tell us which definition of the derivative we have to use. We haven't done any with this first definition, so let's just do one. The limit, and I don't use that definition quite as often, because we wind up preferring the other one. Limit as x approaches A, f of x minus A over x minus A. Alright, so if we're using that definition, we'll do f prime at, on 35 it's negative 2, is the limit as x approaches negative 2 of f minus f of negative 2 over x minus negative 2. And this is the limit as x approaches negative 2. And the f of x is 4x squared plus 2x minus, and when you substitute negative 2 in there, let me do that on the side. That's going to be 4 times 4 plus 2 times negative 2. It's going to be minus 4. It's going to be 16. It's going to be 12. So it's going to be minus 12 all over x plus 2. Now, you can see why we tend to prefer the other definition. This one is easier to understand and easier to visualize, but it's harder to do the computations with. And so I have to get, whereas before all I was left was the h in the denominator, I have to factor out the numerator, and I have to make sure that x plus 2 becomes a factor of the numerator in order to cancel with this. Because if we plug this negative 2 in, I'm going to get, what, 16 plus, 8 plus 4, 16 plus,
My processor?
yeah,
I think it's 4x2 plus 2x.
plus 2x, thank you. Alright, so if I substitute negative in 2, I get 16 minus 4 is 12, 12, and the form would be 0 over 0. So then I have to factor this out. two things have to multiply to be -6. We'll try 1 plus and the other minus. And I want to get a -1. I'll put the 3 here and the 2 here. And then my middle term is going to be -4 plus 3 will be plus 1x. So that's the way that'll factor. Hold it. That's not factoring right, because I have to have x plus 2 down here. That would give me the wrong middle term. This should have been not a plus, but a minus sign. And this should have been a plus sign. So then I'd get 4x minus 3x positive 1x. Okay, so that's the way it would factor. These would cancel out. Now its form is not 0 over 0. And then I'm going to get a limit as x approaches -2 of 2 times 2x minus 3 over 1. And finally, when I substitute the -2, I'm going to get 2 times -4 minus 3. That's -7 doubled is -14. So the derivative, part A, find f prime at -2, it's -14. Then determine equation of the tangent line at the point. All right, so I need two things. I need a slope and a point. So point is -2, and when I plug in -2 into this function, I'm going to get 16 minus 4, which is 12. And I'm going to need a slope. Which I just determined was -14. And then I plug that into y minus y1 equals mx minus x1. So y minus 12 equals -14 x minus -2, and then I'd simplify that down. Okay. Does that answer the question for 35? Everybody okay with that? Any questions?
I have a question.
Yes.
So when do you know to use the limit as x approaches a or the limit of h approaching 0?
At this point, you follow the instructions. And some of the instructions said use one, and some of them said use the other one. This one didn't say which one. So we could choose on this one. So it didn't matter. And I just wanted to give you some experience using this definition to see that it's a little harder because the other one just had an h in the denominator. This one you had to factor out the numerator to get that factor in there, so it cancels out. Okay, any other questions, any other problems?
Gerardo had number 29 and number 43.
All right, let's do 29.
I had a question on number 31 as well, so
Okay,
whenever you have.
well, let's do 29 and 31. All right, both of those are tricky ones because that's a fraction and then that's a square root. I am going to do, I don't think I'm going to have time today. Well, we might have time. It'll depend on how much time we have. So let me do one of these now, and then I'll do the other one as time provided. So let's go to the snipping tool. Let's do 29. What's going on? So we'll do this one. Now this says use definition 2, which is the one that involves h. So we're going to have, and I'll write that out, f prime at a is equal to the limit h approaches 0, f of a plus h minus f of a all over h. So we're going to use f prime at -1. Now notice, if -1 was plugged in for the x here, you would get 1/5, which is how they got the y value. And according to this definition, this is the limit as h approaches 0. Now, -1 is replacing all the a's. And this is equal to now f of anything is 1 over 3 minus 2 times that thing. And when I substitute -1, I'm going to get 1/5. And this is, let's go way back here, equal to let's take that top fraction. This is going to be 3 plus 2, which is going to make 5, and then 3 minus 2h. So that fraction reduces to that over h. So what I want to do is I want to get a common denominator. The common denominator is going to be these two things multiplied together. So this one I'm going to multiply top and bottom by 1/5. This fraction I'm going to multiply top and bottom by 5 minus 2h.
Don't you multiply by 5 over 5, not 1/5?
Oh, thank you. Okay. And then we come over here. This is equal to the limit. H approaches 0. Now the denominators will be the same, so I can just push all the numerators together. 5 minus 2h all over 5 times 5 minus 2h all over h. Now, in the numerator, this 5 and this 5 will cancel each other out. There'll be a double negative over here. So this will become 2h over 5 minus 2h. But instead of putting it divided by h, I'm going to put times and reciprocate this, h over 1 over h. And then these, well, we're supposed to have that. These two will cancel out. And then that's going to equal, now this was supposed to have a limit in front of it. I'm just going to put a capital L for that. Equals the limit as h approaches 0 the only thing that's going to be left is 2 on the top, 5, 5 minus 2h on the bottom. And then as h goes to 0, it drives this whole thing to 0, and I get 2 over 25. And that's the slope of a line tangent, and then you still have to determine the tangent equation of the tangent line. You have the slope, you have a point, use the point slope formula. So that's going to do number 29. And let me stop with questions for here. I think I'm going to have time at the end of class, but I just want to make sure that I can get through today's section. So let's go to today's section next, and then we'll go. But before that, were there any other questions on this? That was clear on 29? All right. So let's go to 3.2, the derivative as a function. And ways to think of slope. The most common way, the way that you were taught for probably many years, was the slope is the rise divided by the run. And that's really more of a way to compute it than to interpret it. When we interpret it and say, what does it really mean, there are 2 ways of looking at it that I really like. One of them is, it's the change in the output each time the input increases by 1. Now this comes from looking at rise over run, but instead of looking at it like, hey, the slope was, it rose 8 every time it ran 2. Well, reduce that to 4 over 1, and you see it rises 4 every time it moves to the right 1, or the output increases by 4 every time the input increases by 1. Now, when we set the input to increase by 1, our mind interprets it more naturally, and it makes more sense. And we'll see that with some examples coming up. All right. The other way is the sensitivity of y to a 1 unit increase in x. How sensitive is the output to the x going up by 1? That's a great way to think of the slope as well. And again, in calculus, we're going to be emphasizing the interpretation of it. What does it mean? So these will be really important to us. So a couple activities. Number 1, describe in simplest and clearest language what the slope represents. We want language that a 3rd grader would understand. So again, if you use technical language, even the word slope, a 3rd grader isn't going to get. If you use rate of change, a 3rd grader isn't going to understand that. We want something really nice and simple. So an A, y is equal to 3x plus 2. X represents days since the dump was emptied. Y represents tons of garbage in the dump. So a sentence describing what the slope represents. So I want you to consult in your groups, and using the group chat, make sure that you know who is the spokesman for your group today. The group leader should make that clear. I'll give you a minute to ponder this, and then I'll ask a group. right, group 3, what do you have for this?
We're thinking every 3 days since the X amount of days it's been dumped. So 3 times each day the dump was emptied, plus 2 from your neighborhood, I guess from your trash can, is how many tons of garbage in a dump?
Um, let me help you a little bit here with, let's make a little table. If you put in 0 for X, you're going to get 2 for Y. You put in 1 for X into this function, you get 5 for the Y. Put in 2 for X, you're going to get 6 plus 2 is 8 for the Y. Can you explain what the 0, 2 represents?
So on day 0, there was only 2 bags of trash.
2 tons of garbage
Right.
in the dump. All right. So, and then what about 1, 5? What does that mean?
That means on the first day, there were 5 tons of garbage.
Okay. And then day 2, there were 8 tons of garbage. Okay. Now the slope is just this. What does that number represent in terms of what's going on here?
So every passing day, the tons of garbage increases by 3.
Very good. So what you're using when you did that, you used this. The change in the output, so how many tons of garbage, so 3 tons of garbage, the tons of garbage increased by 3 every time the input increased by 1 every time 1 day went by. Each day that goes by, so each day 3 tons of new garbage goes into the dump. All right, let's ponder part B. So X is the days since a huge snowstorm. Y is inches of snow on the ground. And then sentence describing what the slope represents so that a third grader can understand it. The simplest possible terms. Go ahead. Work that out into groups. All right, group 6. What do you have?
So we said that after the huge snowstorm, the original amount of inches was 12 inches of snow, but each day it has melted at 7 halves a day.
Then it's melting, okay? And who is talking this? What's your name?
Oh, Daniela.
Danielle. Okay, thank you. Um, let's look at a table for this. When x is 0, we get 20. So Daniela, what does 0, 20, what does that represent?
Wouldn't that be the amount of inches of snow you originally start with?
That's right. That huge snowstorm must have dumped 20 inches of snow. Okay, and on day 0 there was 20 inches. So then if we go to day 1, now let's look at this. Negative 7 halves is the same as negative 3.5. So negative 3.5 plus 20 would be 16.5. Day 2, another 3.5 inches melts. That would be down to 13. You could also just substitute 2 in there. Negative 3.5 times 2 is negative 7. Negative 7 plus 20 is 13. So in day 2, 13 inches of snow. So now, let's put all our focus on this number, because that's the slope. The number in front of the x. Regardless of what the 20 is, just what's this? What is that in terms of this situation? And anybody can chime in here at this point. How would we describe that?
So every day, 3.5 inches of snow melts from the ground.
Okay, that once again is using this same thing right up here. The change in the output each time the input increases by 1. Every time the input increases by 1 day goes by. Each day, so that's increasing the input by 1. 3.5 inches of snow melt. Now, we could have also described this as, because the slope m, you need to put the negative sign with one or the other. And we often put it with the top. You don't have to. You can't put it with both numbers. If you wrote the slope this way, you would tend to interpret it as every 2 days, 7 inches of snow melts. But our minds are not so good at interpreting that. The first thing that we would do to make sense of that is divide 7 by 2 and say, oh, that means it's melting 3.5 inches per day. We tend to interpret and have a better sense of what it means when we increase the input by 1 rather than whatever number is in the slope thing. So we've often learned to do, whatever numbers are there, that's the rise, that's the run, so on. But when we're interpreting it, it's much better to change the input to always go up, be positive at the bottom, and by 1. So we change this instead to, even if it's a decimal, negative 3.5 over 1 for the interpretation. Okay, let's do C. Y is 3x plus 2. Notice that's the same as in A, but this time x is days in the last month the teeth were not brushed. Y is the number of teeth that have excessive tartar on them. And so describe in your groups, and I'll call on your group in a minute. All right, let's go to group 2. What do you have?
Oh, we didn't establish who our spokesperson was. I'm sorry. We have that you start off with 2 teeth that have excessive tartar, and for every day that they aren't brushed, 3 more teeth will have excessive tartar.
Okay, and so if we're just going to focus on the slope, sentence describing what the slope represents, what part of what you described would you then have, and what part would be eliminated?
The slope would be the 3 teeth per day.
Very good. All right, so each day that teeth is not brushed, there will be 3 more teeth with excessive tartar. Okay. Now, this one, of these ways to think of slope, I think this one is most helpful with this. The sensitivity of your mouth to a day of not brushing your teeth. Each day that you don't brush, you get 3 more teeth with excessive tartar. And if this sensitivity was much smaller, you suppose the sensitivity, instead of being 3, was 0.00001. So then each day that you don't brush, you hardly get any tartar extra on there. And so why bother brushing your teeth then? Then if that was the situation, we probably wouldn't have this daily habit of brushing our teeth. After looking at this situation, I wonder, what does the 2 really represent here? Can anybody tell me what the 2 is about?
So you already have 2 teeth that have excessive tartar.
No matter, even if you brush every single day. So if you had 0
Right.
days, you're probably still going to have, a couple teeth with excessive tartar. But that'll, of course, I made all this up. None of this is realistic, tartar and teeth. All right, but sometimes the situation is such that we really want to look at the sensitivity. How much does the one change when the other changes by 1? And does it go up when the other goes up, or does it go down when the other goes up? And that would be a negative slope and all that stuff. So we can change our point of view to whichever is most helpful. So why are we so interested in slope? And we've been really focusing on the interpretation of slope here. Because the derivative, which is the primary concept in all of calculus 1, 2, and 3, that and its inverse operation, which we'll find out to be the integral. Those are the big concepts, the 2 big concepts in all of calculus. But the derivative represents the instantaneous slope. Instantaneous slope is huge. All right. And again, we'll be not only computing it, but we'll be interpreting it a lot. And these 3 different ways to interpret, 3 ways to think of slope, will be handy for us. All right. So this is kind of a natural breaking point for us. So let's pause right now. We'll take our 15-minute break. We will start again. we'll start up again. And, all right, so there's a graph. Here, the graph above is made up of 3 straight line segments. The farthest one to the right looks a tiny bit curved, but imagine that it's straight. I pulled these from the internet, so quicker than me just making them up. It says, draw the graph of f prime of x on the same axis. Alright, now you'll probably have no idea what I mean by this, so let me do this first one for you. Okay, so the graph of f prime. Alright, so the title of this, and let me just come back up to here. The title is The Derivative as a Function. And the practice quiz that we looked at over here is we can look at derivatives as functions. So if the function had a slope of 7 all the time, its derivative has got to be 7 all the time. If the function was a horizontal line, its derivative is the slope of that horizontal line, which is 0, and so on. So we can use that same kind of analysis here and say, hey, when x is between negative infinity and negative 1, so anywhere up to negative 1 where it's blue, the slope is always, well, every time I move to the right 1, I go up 1. It's the rise whenever you go to the right 1. How much the output is increasing or decreasing, how much the output changes every time the input increases by 1. That's the slope. So the slope is 1, so the derivative must be 1 for all these same inputs. From negative infinity to negative 1, the derivative must be 1. Now, right at negative 1, the derivative does not exist. So I'm putting a big open circle there. How come the derivative doesn't exist at negative 1? Because remember, the derivative represents the slope. And if you approach negative 1 from the left, you're going to get a slope of 1. But if you approach negative 1 from the right, you'll get a slope of 0. The limit from each side is different, so the total limit doesn't exist. The derivative is the limit, so that limit doesn't exist when x is equal to negative 1. Now, let's say for the red portion, the slope is 0 there. It rises 0 every time we run to the right 1. So, again, it's not slope, the derivative is not defined at this endpoint. The derivative is not defined here because you're going to get 2 different values of slope when you approach from the left and the right. But in between, it is 0. And then, from here to here, imagine that was a straight line. Every time I move 1 to the right, it looks like I'm going up 1, 2, 3. So imagine it's a slope of 3. So then, I just go like this. So what I've done is I'm looking at the derivative as a function of x. I'm looking at the totality of it. And I could write this derivative, the equation of the derivative, but we're starting off graphically, and we're just drawing the graphs of the derivative functions. So this, what's in gray, is the slopes of these different colored figures. Any questions? Yeah. All right.
So,
Yes.
in general, then, if you have a function that that has like a corner or like a pointed peak, then you won't have it won't be differentiable at that point.
That's correct. You won't have a derivative at that. In fact, a function that has any kind of sharp turns, like straight line turns, it's going up like this, and then it sharply turns. Right there, it's not going to have a derivative. If it had smoothly turned, it'll have a derivative. But if a real sharp one, it won't. Another way is we kind of call them cusp points, like this. Right there, where it kind of abruptly just changed, it won't have a derivative there either. Because from the left, you'd see the tangent line would be positive, and from the right, the tangent line would be negative, and doesn't have a single tangent line at that point, right there. All right, now, if you think you've got it, let's go to this one. It says for the graph above, draw f prime on the same axis. So, let me give you a minute. Go ahead and draw f prime of x. Alright, so this one, they actually tell us what the equation is as well. So on the far left, we didn't even have to say that, oh, every time I move from, like, you look at where it intersects. Like right here, it looks like it's intersecting grid lines. And then every time I move to the right one, it looks like I'm moving down 2. So it looks like the slope is -2, which coincides with the equation right here. So from negative infinity to 4, we are getting a slope of -2. And from 4 to infinity, my slope, every time I go to the right one, well, let's go between where it crosses grid lines. 0, 0, and then if I go 2 to the right, up 1. 2 to the right, up 1, that works. So it's going, rise is 1, run is 2, it's 1/2 is the slope. And that agrees with this equation right up here. So the slope is 1/2. So that becomes the height. So if this is the curve f, this is the curve f prime. We can draw a function and its derivative on the same grid, and this is telling us what the slopes of this line are at every point. By looking at the height of f prime, that's the same as the slopes of f. Alright, let's go on. Number 6.
Professor Shankin, I'm
Yes.
sorry. I had a question about that graph right there.
Yeah.
So you're looking at the function of the derivative on a graph.
Yeah.
You wouldn't be able to, I guess, extrapolate from that if there was a constant in, like, so you could say, okay, for example, from x is less than 4, you know your function, I guess your parent function would have -2x as its slope, but you wouldn't be able to extrapolate from that it has an 8 y-intercept, correct?
That is correct. If we were going backwards, if we had the slope and we were trying to reconstruct the line, what you called the parent function, nice name for it, we would know that it would have a slope of 2, but we would have no idea where its y-intercept would be. And so going backwards is more complicated. we would only have one piece of information, its slope, not its y-intercept. Good point. All right, and we'll be doing some of that in a little while. We'll be going in the reverse direction, but that's important to note that you don't get a unique answer when you go in the opposite direction. All right.
So when you
Yeah.
do the graphing, the height at 1/2
Yes.
is describing the derivative of the left or right? I thought it was the left line.
All right, so this f of x has a slope of 1/2 when x is greater than 4, so that's the right half. So that has a slope of 1/2, while this
Oh,
has
I
a
see.
slope
Okay.
of -2, so that's why the height of the derivative function.
So
is
then
negative.
would, on the left-hand side of 4, would that also correspond to the line f and then derivative f of prime?
Yes, yes. The function f that equation is that part of f. This equation is this part of f. But the whole kind of 90-degree angle bend there, that whole graph is f. And there are two parts of f prime down here. Thanks for pointing that out. All right, let's go to number 6. From 0 to 4 on the x-axis, where does this function have a derivative? And you could also reverse it and say, where does it not have a derivative? And on this one, I want you to consult in your groups, and I'm going to pick on a group in a minute. Okay, group 4, what do you have? Anybody here in group 4?
Hello, hello.
Yes.
Okay, so there isn't a derivative at x equals 2 because of that peak.
Very good. At this point right here, we got a problem.
Yeah,
Okay. And who is it that's talking?
Josh.
Josh. Okay.
Yeah,
And is there any other?
maybe x equals 1 because it's not included in it.
Now that one's going to be, we're going to have to really think about that.
Okay.
Does the derivative exist there or not? So clearly at 2, the derivative does not exist because, let me show you, the tangent line from the left appears like this. The tangent line from the right is this slope. That's just going to nick the curve. And you're going to get two different results. So 2 different tangent lines clearly, and that's, again, this one is called a, let me get my eraser. This is called a cusp point. derivative does not exist. Let me first ask, when x is equal to 1, does the limit exist?
Yes, it does.
At x equal 1, the limit as x approaches 1 of the function, well, it's not f, it's g, is equal to 3. Because as I get closer and closer to 1 in here, we get closer and closer to a height of 3. Just, you're not allowed to get to that destination. So, if the limit exists at x equal 1, does the derivative exist at x equal 1? Does anybody have an opinion about that?
I think it does.
It tends to make sense that g prime of 1, since the limit exists, maybe the derivative exists. But g prime of 1, let's use the limit definition as h approaches 0. G of 1 plus h minus g of 1 over h. Now, g of 1 is the height when x is 1. And that doesn't exist. G of 1 appears in the derivative. And it turns out that even if this had a definition of g of 1, like suppose there was a filled-in circle up here, and then it was what we call a whole discontinuity, that would still, the derivative would not exist, because g of 1 is part of the computation in this. And so, where does this function have a derivative? The answer to that would be the open interval from 0 to 1, union from 1 to 2, union from 2 to 4. It does not have a derivative at 1, it does not have a derivative at 2. At 2 it's a cusp point, at 1, just because there's a hole there, the derivative will not exist. Okay. Now, this is different than continuous. We can see that at x equals 2, the function is still continuous. At x equal 1, the function is discontinuous. You have to lift your pencil to draw it. But discontinuous is not the same as derivative non-existing, and so on. They're separate and distinct topics. All right. Well, let's go back to number 7. Before I go on, any questions on 6? Everybody clear on this? All right, number 7. Now it's going to get a little tougher. Let's sketch the graph of f prime on the same axis. And now we don't have a straight line segment to get its derivative. All right. To get started on this, to sketch the graph, we're going to jump to number 8. We need to come up with some guidelines on how to graph f prime if you're given a graph of f. And so I have some questions here. Now, this is a theoretical function. It doesn't relate to number 7. If f has a slope of 0 at x equal 4, then what must be true about the graph of f at x equals 4? And then you're going to answer what must be true about the graph of f prime at x equals 4. We'll start with part 1. If f has a slope of 0 at x equals 4, what must be true about the graph of f at x equals 4? Discuss it in your group. I'm going to call in a group in just a moment. All right, let's go to group 5. What do you have? What must be true about the graph of f at x equals 4? Anybody in group 5 here today? All right, let's go then to group 6. What do you got? Anybody from group 6? I hope you all are still there. Oh, yes.
We haven't discussed it.
Okay, do you have an idea? And you can always say pass on any, if you're not sure. But if you got an idea, you can chime it in. All right, let's go to group 2.
If the graph of f at x equals 4 has a slope of 0, what I put was that your tangent line at that point would have to be run parallel to the x-axis.
Okay. The tangent line is parallel to the x-axis. And if the tangent line is parallel to the x-axis, what might be happening to the general graph of f?
It's in the case of a parabola, it would be identifying a maximum or a minimum point.
Very good. All right. See, if we were going like this, then the tangent line at 4 would be horizontal. And if we were like this, and it's not just a parabola, it's any kind of dip. So it's the bottom of a valley or the top of a hill. So the technical answer here is tangent line is horizontal. And what that usually means we're at the top of a hill or bottom of a valley. So if we had a graph that looked something like this, we would say, the tangent line is 0 here and here. Tops of hills and bottoms of valleys have tangent lines at 0. Now, notice that I use the word usually. It's possible to have a tangent line 0 and not be at the top of a hill or bottom of a valley. But that's rather unusual. It's rare. And let me show you one of those rare cases. Could look like this. This would imagine a stock function that's going up, 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 up. And now you're getting sad because it's not going to be making so much money anymore. And right in here, it gets horizontal. But if right at when it's horizontal, it reverses its trend and starts going up again, then you could have a horizontal tangent line. And it not be a top of a hill or bottom of a valley. But they're usually at the top of a hill, bottom of a valley. Something very unusual has to happen. It has to change its tendency at just the right point for that not to be the case. So usually, to find where the derivative is 0, f has a slope of 0, it's really easy visually. You just look for tops of hills, bottoms of valleys. All right, let's go to part 2. F has a slope of 0 at x equals 4. What must be true about the graph of f prime at x equals 4? Let me give you a minute to think about that, discuss that in your group. I'll call on a group in a minute. Okay, group 3. Any ideas? And you can always say pass.
Not sure what the question is asking. Is it asking for like a function of f prime?
At x equals 4, we know that the graph of f has a slope of 0. So it might look like either this, it's the bottom of a valley or top of a hill. And then what must be true about the graph of f prime at x equals 4? And it's a kind of a tricky conceptual question. Let me go to that. At x equals 4, we have an x.
Does that mean that it's a derivative?
Yes, when we're graphing the derivative, we have an x-intercept of f prime. All right. Remember when we were graphing the derivative? When you are horizontal, that becomes 0 for the height of the derivative. If your slope was 1, your height of your derivative was 1. But if you're horizontal, any place you're horizontal in f, then that's an x-intercept for f prime. Now this has everything between -1 and 1 is an x-intercept for f prime because the whole graph is horizontal in that region. So when we come down to here, if I was drawing f prime,
Would it just be a dot at 0 in that case?
That's right. It would be a dot at 0. That's correct. So when we come up to this graph, let's look back to number 7. Sketch the graph of f prime. The first thing we look for is, where is the slope 0 for f? Well, that's at tops of valleys or bottoms. Bottoms of valleys or tops of hills. This has a hill, and we have a horizontal tangent line right there. Since we got a horizontal tangent line right there, that's going to become an x-intercept. A dot right here on the x-axis. Okay, so that's the first thing you do, is you find tops and bottom, any horizontal tangent line, that becomes an x-intercept for the derivative function. If it was like this one, it would have 2 x-intercepts. We would make 2 dots. Right. So now let's go to part B. If you are sure that you found all places where f has slope of 0, which is usually tops of hills, bottoms of valleys, horizontal tangent lines. It doesn't have to be top of hills, bottom of valleys. It could be this strange case that has a horizontal tangent line like that. But most of the time it's tops of hills and bottom of valleys. Then what must be true about the graph of f prime between consecutive x-intercepts? Now, let's look at,
So would that mean that it's half of the x-intercepts?
kind of like the halfway point between the x-intercepts?
Yeah.
All right. Something special is going to happen at the halfway point between the x-intercepts. And we're going to get to that in a little bit. Before I get to that, though, let me also just point out that between consecutive x-intercepts, like on this one here, what must be true about the graph of f prime between x-intercepts? F prime must be entirely above or below the x-axis. Now, why does it have to be entirely above or entirely below the x-axis? Why couldn't f prime be partly above the x-axis between these consecutive?
Because they have to cross the x-axis.
That's
in
right.
order
It
for
would
it
have
be
to
an
cross the x-axis if it was partly above and partly below. And if it crossed the x-axis, that's another place where you have a slope of 0 of your original function. But you've already found all the points that had a slope of 0, so you can't have any more places where you have slopes of 0. So the graph must be entirely above or below the x-axis. And let me get my cursor here. Otherwise, we create another x-intercept.
So, Professor Shankin, so then, like, am I interpreting this correctly? So if we're looking at the graph that you had that looks like it's a negative some x squared.
Yes, this one.
So if I'm looking in relation to the x-intercept, everything to the left of 4 would show positive slopes that are becoming less and less positive. Is that correct? And then on the right side.
Okay. Yes. We are going to look now. Let's get right to your analysis, Francis. So let's make sure we're good on this point there on B though, 8B. If we've identified all of the places on F that have slope of 0, those become the x-intercepts of F prime, and then we must be entirely above or below the x-axis on the different sides. So on the left side of this one, we can't be both above and below the x-axis. If we were, we'd be creating another x-intercept. So on the left side of this, Francis started to talk about that we are going to be seeing, see, this is a positive slope. Positive slope. But what are we noticing? They're not quite as positive. If you own stock in this company, you'd be very happy here because you're going up so fast. As time goes on, you're still happy because your stock price is going up, but it's not going up quite as fast. It's not going up nearly as fast way over here. Finally, it's going horizontal for a moment right there before it goes to falling, and it's now negative. All right, but what's happening to the left of this is the slopes are all positive. Slopes are all positive. But they are getting less and less positive, and finally they get to a slope of 0. All right, and if we drew that, they are positive slopes. Like over here, the slope might be like 6. It might be way up here. And then over here, the slope might be like 3. There. And if we connect all these, and when we get to here, finally the slope is 0. Now, to the right of this, we see that the slopes are all negative. And the further you move to the right, the more sharply it goes downhill, the more negative you get. So, slopes are all negative. It couldn't be both positive and negative on this side, then it would create another x-intercept. Slopes are all negative, and the further you move to the right, the more you get negative. And it turns out like this. And from early graphs of functions that look like parabolas, when they started graphing the derivatives, they started to notice, wow, parabolas are second-degree polynomials. And when we take the derivative function looks like to be 1 degree less, instead of a second degree, a first-degree polynomial, which is a straight line. Any questions, comments? It gets rather conceptual here, graphically.
So then, is the overall derivative going to be something that's going to be only in the degree 1?
That's a good question. We're going to look at the relationship. Sometimes it's going to be degree 1, but sometimes it's going to be higher. If the original function was more complicated, the derivative function is going to be more complicated. But it looks like so far, perhaps the relationship is that it's 1 degree less. So if this was a parabola, which is a second degree, then the derivative is 1 degree less, which is a straight line, first degree polynomial. All right, let's go to number 9. How to graph f prime when given a graph of f. Step number 1. Find where f has slope of 0. Now, I really should put usually tops of hills, bottoms of valleys. It doesn't have to be a top of the hill, bottom of the valley, but most of the time it is. Okay. These are x-intercepts of f prime. Step 2. Between pairs of x-intercepts of f prime, the graph of f is entirely above the x-axis or entirely below the x-axis. Otherwise, it would be creating more x-intercepts. And then we keep going from there. All right, so number 10. Sketch the graph of f prime of x on the same axis. So there's the graph. I'm going to give you a minute to just work on your own. Try to sketch f prime, and then I'll do it in just a minute. Alright, so before we start, does anybody recognize this curve? This is y equals what?
X
Cubed.
Very good, y equals x cubed. And we'll do the first step. The first step, find where f has slope of 0. Where does it have slope of 0? Right here. So that's going to be an x-intercept of f prime right here. Now, it only has one of these, but if it had more than one, then we'd go in between each one. Okay. Now, since there's only one, we just go to the left of it. What must be the case is that all the slopes are positive or all the slopes are negative to the left-hand side of it. If it was both positive and negative, we'd be creating another x-intercept. So, to the left of it, what are all the slopes? Are they all positive or all negative?
All positive.
They're all positive. Whoops. You can see them here. The slopes are positive, and the more you go to the left, the steeper they are. All right. So, this one, they are positive, and the more you go to the left, the steeper they are. Turns out, go like this. Now, let's go to the right. The slopes have to be either all positive or all negative again. If it was both, it would be creating another x-intercept. What are all the slopes over here to the right? They look to be all positive again. You'd be happy if you bought stock in this company. The further you went to the right, the higher they would be. And when they did detailed graphs of third-degree polynomials, they got second-degree polynomials as the derivatives. So this is f prime. It appeared to be 1 degree lower than the original polynomial.
So what you're saying is, if it's like, let's say, x to the fourth, the derivative would look like a graph of x to the third, x to the third.
That's correct. It would have not exactly x to the fourth going to x to the third, but if it was some fourth degree polynomial, the derivative would be some third degree polynomial. That's right. Okay, and then let's go to number 11. All right, follow the steps. Make all your x-intercepts for f prime, and then in between each x-intercept, It's got to be either all positive or all negative and so on, and try to make the shape. So let me give you a minute on this. So this is the graph of f, and to do f prime, I first find out, here's the top of a hill, that's an x-intercept. Here's the bottom of a valley, that's an x-intercept. Now this one is neither a top of a hill or a bottom of a valley, but it does have a horizontal tangent line. So that also. So I get 3 x-intercepts for my f prime. Everybody good with this so far? Next, I look between consecutive lines. Let's go in between -1 and 0. Now, what must be true about the slopes? They must be either all positive or all negative. Because if they were both, it'd have to go through 0, which would be another x-intercept, but we have all the x-intercepts. So what are all the slopes over here? If you bought stock in this company between -1 and 0, you'd be happy because it's going up the whole time. Now, let's go approximately halfway between these two. Very often, at about halfway between, you see that we have about the steepest that it ever goes up. So it's kind of like if you were climbing this hill, if you were a rock climber and you started down here, you know, where is it the steepest? Where are you going to need the most equipment? It's probably right here. If you're climbing up this hill, that's where it's the steepest. Now, where in its positive slopes this whole time, but what is that highest steepness right here? If you had to make the line for that, so let me go to a different color. The instantaneous slope at the steepest point, right here, looks kind of steep. Every time you go to the right one, I might be going up like 4, say. Let's say that m equals 4. If that was the case, m is maybe 3. If that was the case, then right above here, I would go to my highest height of about 3. And then we would go, notice the steepness, it's getting steeper and steeper, and then it's getting less steep and less steep. So it goes from here up to here, and then back down to here. Now, let's do for a next consecutive pair of x-intercepts. The slopes, are they all positive or all negative in this gap? Well, it looks like they're all positive. If you own stock in the company, you'd be happy. And where is it steepest? Very often it's about halfway between these two. There. So again, if you're a rock climber, that's the steepest spot right here. And the slope, instantaneous slope, maybe it's not quite as high as that one. Maybe it's only like m equals 2. So then we might go at the halfway point, not quite as high here. And this comes back up. And we're coming down. All right, now let's go to the two end intervals, the farthest right portion. The slopes must be all positive or all negative. But what are these slopes? They are all negative now. You'd be sad if you own stock in this point. And the slope is 0 here, and then it's getting a little bit negative. It's getting more and more negative as we go on to the right, going like this. When we go over here, what are the slopes over here? If you own stock in this company, remember, you'd always be moving from left to right. You'd be going downhill, so it's negative slopes. And the further to the left you go, the further negative you are. So it sends you down like this. And thus, we get the shape of our graph.
Do the peaks and valleys in the derivative graph or the F prime graph then represent like the moments where it looks like you're kind of shifting, not direction, but like at like moment, like what you were talking about, where it kind of plateaus and then it starts to become less positive?
That we're going to get into much later on in the course.
Okay.
And we're going to have a special name for those points, the peaks and the valleys of the derivative. But we won't get into that until we get into later on. It's called the second derivative. And there'll be a special point called an inflection point. But you have great anticipation. That'll be what's coming, but not for a while yet.
Okay. No, thank you. It just looked really interesting to see how it relates with
Yes.
the. Okay.
Any questions before I move on?
So,
Yes.
algebraically, would you find the slope between -1 and 0 and then find where the highest peak is?
Rough, crude approximations are all you need for this. And if you made this hump higher than this hump to the left, I'd still give you credit for it. As long as you stayed above the x-axis over here, stayed above the x-axis over here, and so on. If you're getting really detailed, though, you can get a little more precise. That's kind of what I was showing you. Okay. That's our last one that we're going to do. Now, much of the homework on this is graphical. And it's going to have you, it'll start you out with problems that are they're all straight line segments. And then you'll be moving on to where it gets more like this and so on. And you're going to get some trickier ones. But you'll be making the graphs for these as you go along. All right, we do have some extra time now. So, reminder, Thursday is the exam. So, no need to meet on Discord. It will open up at 11:30. There's no class that's going on Thursday. And then have your answers uploaded by 1:45. At 1:45 it times out. It doesn't let you upload it into the test thing, so please have it uploaded before 1:45. If something crazy happens, like you have kids and some emergency happens with a kid and you have to go and tend to them and you just can't get it in by 1:45, then just explain your situation and email it to me after that time period, and that would be fine. Again, you're on your honor to take it under the same conditions that we take exams had this been at the community college. So do not use a graphing calculator, use a non-graphing calculator. Do your computations, show all your work, all your steps. Okay. Any questions relating to the exam?
I noticed last exam there was the PDF and then the Microsoft Word version, and
Yes.
I forget which one, but one of them didn't have all of the question displayed, and so is there one that's better to download than the other?
I was never aware of that. Was that the case at one of them?
That was for me. I forget which one it was though.
The one for the Microsoft is Trio, which doesn't download the special characters, so I usually use PDF.
Maybe it was the limitation of the receiving software. Okay. Yeah, the PDF should be foolproof. The only reason the Microsoft Word document is there is that some people like to type out their answers, you know, the portions that can be done like that, and then people could upload it back in Microsoft Office, Microsoft Word. All right. Questions? Any other questions regarding the test? There's also a bunch of homework that's due Thursday. And all right, questions on homework. What was another question? So I don't have to scroll back through everything in Discord.
Number 31.
31.
That was the one with the square root.
Okay. Let me look over here. So, and that was in 3.1. 31. All right, let's do that on the, I'll use my camera and my whiteboard here. F of x is equal to the square root of x plus 3, and the point P is 1, 2. Okay, and we need to do part A, use definition 2, find the slope of the tangent line. So we need to find f prime at 1. And we're going to use f prime at A is equal to the limit as h approaches 0. Tells us to use the second definition, which is the h1. F of A plus h minus f of A over h. And so f prime at 1 is I just replace all the a's with 1. And 1 plus h goes in. What this function really means is f of anything is the square root of that anything plus 3. So 1 plus h is going to go in that parentheses. And so the 1 and the 3 will join to be square root of 4 plus h minus, and when I put a 1 in there, I get 2, because I get square root of 4, which is 2, all over h. Alright. This, its form When I substitute 0 in, I get 0 over 0. It's the indeterminate form. I have to simplify this. The only trick I know when it involves the square root is multiplying by the conjugate. And if this doesn't work, I don't really have anything else up my sleeve. That's what I'm going to try. Hope it works. And I got the reason why I multiply by the conjugate is the only way for the middle term to cancel out. And when I FOIL this times this, 4 plus h. Plus 2 minus 2 minus 4. I don't multiply out the bottom because it's that h that I want to cancel out. Now I notice that this 4 and this 4 cancel. And these two cancel. So I get h. It's all that's left on the top, which is perfect because that's what I wanted to have cancel on the bottom. And then cancel those. Now, as h goes to 0, drives this thing to 0. So I get 1 over square root of 4 plus 2, which is 1 over 2 plus 2, which is 4. That's my slope. Thus, f prime 1 is equal to 1/4. That's my slope. My point was already given, 1, 2. So I'm going to use my point slope formula. This is part B now. Y minus 2 is 1/4, x minus 1. And then come up here, y minus 2 is 1/4 x minus 1/4. I add 2. Y equals 1/4 x plus 1/3. There's the equation. That's the answer for B, while this was the answer for A. And then when I get one of these, what I always like to do is to put both the original function and the tangent line on the same graph. And an easy place to do that is Wolfram alpha. So I will go to Wolfram alpha. Equals square root x plus 3, and then y equals 0.25x plus 1.75, and we'll graph both of these. And right this was at 1. It should be nicking the curve. It's the tangent line to the curve, and it looks exactly like it should when I plot them both. All right. Does that answer questions? Anything else? All right, we'll stop here.
So,
yes.
so for these problems, you have to graph them too?
No, I just did that for my own benefit. The only thing that was required was part A and part B, but the graph kind of is a nice way to check the work. All right. We will stop here. I'll turn off the videotape. I'll see you, well, I'll be grading your tests this weekend, and you'll be working on them tomorrow.